Thanks for being here. It's a lovely crowd. I wish we had so many people in Auckland, where I come from, doing functional programming. So my talk's about how I use Haskell for doing radar target tracking. Radar target tracking and Haskell seem to be two very disparate worlds, but they've managed to intersect for me at work. And sometimes my work seems to be a product of, or rather the marriage, a child created from the marriage of C++ and Haskell. And it seems that C++ likes to disown this child and thinks that it's an accident, whereas the child is quite well behaved, which is a surprise to C++. I don't know enough about Haskell yet to be able to say what Haskell thinks of the child, but Haskell has been a great help in what I do, and I'm here to talk about how I benefit from it. So my background is in embedded systems, low-level bare metal systems, kernels, operating systems, file systems. I've been using C and C++ for these things for most of my career, and these are lovely languages. They excel in allowing people to be frugal with resources and being very low-level in being able to express resources. The trouble with being frugal is one never knows if one has gone too far. And the trouble with being low level is that sometimes you can miss the forest for the trees. And maybe that has happened a lot in my career for me. But recently I've been employed at a company that does marine electronics. So they do, think radars, think ships, think navigation aids, think tracking over distances of 100 kilometers in all directions, and that's what I do. So my work is to create algorithms for target tracking in the context of radars. And real data has noise, and my task is to filter the noise away and infer the key parameters of data. And I derive a lot of benefit from using Haskell to prototype my filters. So that's what I'm here to talk about. So in this talk, I'll go a little bit into what the problem estimation entails. And it's a bit of math, but it's fun. And then I'll go into how I use Haskell to model my work. And hopefully there'll be time at the end for a practical demonstration. So filters. Well, separating signal from noise can be done in many ways. Most commonly, it's done using digital filters. Filters are simple algorithms which try to infer information. So given a set of observations, they try to infer the key characteristics of the data. So here's a simple filter. It's a trivial filter. It's an averaging filter which takes a sequence of inputs, y's in this case, and simply computes an average of the input. It's intentionally trivial because the point is to show how to form an intuition about estimation or filtering. And the details of the math of the filter don't matter very much beyond the intuition. So in this case, the averaging filter gets a sequence and computes an average over the entire history. And here's how it looks in practice. So given, in this case, time on the x-axis, position on the y-axis, it's a single-dimensional position, a very simplified example. So in this case, the red dots correspond to observations over time, and you can see that the blue line tries to approximate the observations by taking an average at each instance of all the available history. And initially, the blue line is wiggly, but it settles down very easily, very quickly to the actual data, which is centered around 0. And that's typical of filters. So it is not necessary to compute an average by keeping all the data. An averaging filter has a recursive solution, and here's an expression for it. So in this case, an input coming in, the yi, is compared against the previous average, the xi minus 1, and that difference is the innovation. That's the newness that the filter is witnessing. And this newness, this innovation is scaled down by I. And that becomes the delta for computing the new average. And we store that in xi. Yeah, so if you do your algebra, you'll find that this computes averages recursively. This xi serves both as the average and also the input, or rather the state for the next iteration of the filter. So that's a fairly good filter for a vessel that's stationary, and indeed we use it. The trouble with this filter is that as I goes larger, as the history accumulates over time, the filter does not survive a delta, which means if there is a change in the input for any reason, let's say the sensors recalibrate, or because of the tides the vessels move a bit, the filter takes a long time to adjust to the new mean. And depending on the amount of history, it can be very long. And that's obviously a problem. So a simple way to fix that is to limit the I, limit the history from growing too large. And here's an example of how we do it, a fixed memory filter. So in this case, we sample data coming in, the Ys, but then we only keep a window, a sliding window of the data, and average over that. And here's how it looks over the same input. So in this case, the blue line has managed to respond to the change, to the delta, and has ramped up fairly quickly. The downside is that in this case, it is wiggly. It is not as smooth as the previous averaging filter we saw. And indeed, there's a trade-off. Depending on the size of the window, if we have a large window, then the line becomes smoother at the expense of not being agile, which means if the window is too large, the filter does not respond soon enough to delta. But if the window is too small, it is responsive, it is agile, but it's noisy because it's trying to pick up noise in the hopes of detecting maneuver. Yeah, so that's the kind of trade-off a filter designer has to make all the time. And here's a recursive solution again for this filter. And in this case, you will see that the input yi is being compared against the oldest in the sliding window. So that becomes the innovation. And again, the innovation is scaled down by the size of the window, and that becomes delta to compute the new average. So that's typical of filters, to compute an innovation and to work with it to compute a new value. Yeah. Now, a limitation of the fixed memory filter is that the window is fixed. And that can be remedied by a fading memory filter. This is a beautiful filter. It's a dream filter because it doesn't retain much state, and yet it retains a bit of everything, a bit like our own memories. And so what happens here is that the look back or the window of this filter depends on a parameter called alpha, which is between 0 and 1. The larger the alpha, the more look back it has. And so at every step, an input comes in and is scaled down a bit. But then it is merged with the faded part of all available history. And that's a beautiful, I mean, this is the advantage of this filter is that you can vary alpha over time or on the basis of input and get different effects. If the input is varying, then alpha can be small so that it is more responsive. If the input is stable, then the alpha can be large so that the output is stable and has less noise. So that's what a filter designer looks for. And so a lot of filtering in real world can stop right here. Scientists and engineers use these simple filters as a starting point for almost all data processing, and they work. And often scientists, or rather often practicing engineers feel guilty about using these simple filters because they leave you with a sense of maybe there should be something more there's something more to be done. Indeed, it is possible to do more. In general, filtering is trying to solve the problem of regression, in this case, polynomial regression. So given a set of data, a filter tries to minimize the distance of the data from some polynomial. In this case, a straight line, but it doesn't have to be a straight line. It can be any polynomial. And it doesn't have to be Cartesian distance. It can be other kinds of distances over time. So a filter is essentially a minimization problem being solved. Over time, we can use different kinds of polynomials to fit data. And that's my job, to infer the polynomial, to be able to adapt to changing polynomials over time. And this leads to a class of filters called Kalman filters, where a certain amount of tolerance is allowed for the polynomials to change over time. And all of this can be done recursively, right? So before I move on to the other part of this talk, I want to summarize what the key insights of filters. So filters are trying to do minimization, essentially. Filters are trying to do a trade-off between agility and noise. Yeah. And they need to be tuned a lot based on real data or based on simulation. And that's a big part of my job, to train my filters to respond to different kinds of maneuvers. And thankfully, filters often have recursive solutions, so that I don't have to save or retain a large amount of data from the history. Because they are recursive, I can use a simple state-based solution or a step-based solution to implement my filters. Yeah. Now, given all this, Haskell is a huge help for my work. Haskell allows me to think generically about my filters. Haskell allows me to, or rather leads me to discover the properties of the data or of properties of my filters. And that's what I want to get into in this talk. So here's an example. At the core, a filter, since it is recursive, a filter can be thought of as having an operation called single step, where here's the type signature of the single step operation. But single step takes in an input, A in this case, that's the type, applies that input to some state to produce a new state. That's at the core of a filter. This is what exists. Yeah? And here's how we can use it in the context of the averaging filter we just talked about. So an averaging filter can be thought of as keeping an averaging state, which is made up of a double and a count. A double in this case is an instantiation, but it could be anything that is being filtered. So an averaging state is a double and a count, and the single step takes in a new input, a double, applies it to the averaging state to produce a new averaging state. Yeah? The implementation doesn't matter at this point. So together with single step and initial state, we can think of computing averages using this very simple formula. Averages is essentially a fold operation or an accumulation of single step applied to all the input, starting from initial state. Yeah, so this formula here at the bottom captures what filtering does. The output of this is essentially a sequence of states or sequence of averages, right? So let's look at single step one more time. Here's the type signature. Given an input of type A, it goes from an S to another S, a state to another state, which means single step given an input is a state transformation. This state transformation can be considered to be like a state monad in this case. So I can rewrite single step to read like, given an input, it produces a monadic transformation. And I choose to rename that monadic transformation using filter. So that's the signature of single step. Haskell is already making me think generically. Had I been limited to C and C++, I would have been lost in giving the details at a very low level for various operations like this. Yeah. So let's formalize the relationship between S and A. So S and A, S being the state and A being the input, are not completely generic. It's not possible to have any S combined with any A. So S and A, in this pair, S determines A. And I can formalize this together with the APIs into a type class called filter state. So filter state is a representation of a filter, of any filter. Any filter has a state which satisfies, or rather has an API for single step and initial state. Very, very simple, basic declaration. But this has big consequences, because then I can say all filters need to satisfy this, and all filters can be interoperated. And we'll get into that. Yeah. So, given the context of filter state, let's rewrite our averaging filter. Once again, this is a trivial filter. A real filter will be far more complex, but it serves to demonstrate. So averaging state for position, let's say, it can be written in the context of filter state. So averaging state, which represents the averaging filter, is an instance of filter state, where single step takes in a position, gets the previous value of the average, computes the new average. Recall the formula was the recursive formula we had already looked at previously. So computes the new average, puts it back into the state, and then returns the averaged position as a byproduct. It looks like a lot of code, but actually most of it is just mechanics, and most of it is a bit bloated because I wanted to make it clear to see. So this is an instance of how filter state has been used to create an averaging filter. Now, what have we achieved, or what have I achieved in this process? I've said single step takes an input and produces a monadic transition, a state transition. This state transition is actually a monoid, which means it can be composed, it can be added. Two state transitions can be added to form a new state transition, composed to form a new state transition. It's actually a semigroup. This single step A, this operation together with the set of states is a semigroup. And this kind, it's also called a transition monoid. So given that, I'm led to an API called multi-step using traverse. So given any traversable sequence as an input, I can use traverse of single step to form a multi-step. So Haskell is leading me to discover properties. Yeah? So given a sequence of inputs y's, I can monoidically add all the state transitions so that given an initial state, I get a final state, but also a byproduct of, as a byproduct, I get all my averages. And to make the API more useful, I've wrapped multi-step so that all things become easy to use. So multi-step, in this case, has been wrapped by filtered using. And my final application reads like this. Given, to compute the averages x's from any input y's, I'm essentially doing y's filtered using the initial state of some filter. Terse, easy to read, easy to use. I can change filters. I can replace, so all of these filter states are instances of the same filter state type class. So I can replace filters with one another. And that's what I get. Composition, all the plumbing done by Haskell, and I don't have to worry about its correctness. Now, I'm not limited to single state transitions. I can actually compose my state to be multiple states, which means imagine writing a filter which is good for both stationary vessels and linearly moving vessels and turning vessels or doing some other, or accelerating vessels. So that's a composition of different kinds of filters. And I can do that. I can compose multiple filters using the same strategy. Here's an example where I compose the constant velocity filter, a very commonly used filter, with a stationary filter. So my composite state is using constant velocity and stationary together with some weights. The weights are used to blend the results, and we'll look into that shortly, but I have this freedom. Each one of these filters can be run either independently or composed. And here's a little bit of code which shows how I can make a composite filter. So the composite filter state is again an instance of filter state, which means it itself is a filter just like any other filter. It receives an input, it extracts the previous state, but then progresses each of those states using the input to get new component states and new component averages. It computes the likelihood of each of those components using some statistics. And the details of that don't matter at this point. And then computes new weights based on likelihood. And then finally, it puts away the combined new state and also returns a merged position based on the weights that it has computed. So it's blending the results of multiple filters depending on their likelihood. I'm not limited to which filters I use. I can have an arbitrary tree of filters. And that's what I do. I have different kinds of filters composing with each other. I have constant velocity filters with different parameters. I have stationary turning filters, etc., in a tree of filters. And all of these filters are progressing depending on the same inputs. And I blend them to get my final results. Haskell makes the plumbing trivial for me. I mean, the code that I've shown you so far is nearly all the code that I need from Haskell for plumbing things together. And then that leaves me to focus on single step. I focus on writing the single step of each filter. It takes me days, weeks to try things out with every new filter, with different kinds of data. And that's where I spend most of my time. Now, to get something working finally, here's what I do. So I model filters using math and Haskell. I prototype them in Haskell. And I test using property-based testing. Once I'm satisfied with the filter, and that could take weeks, once I'm satisfied with the filter, as a final step, I translate my filters into C++. It takes me only a day or two to write corresponding code in C++ because I've already understood what I need to do. It takes me less time to write Haskell plus C++ than it takes me to write in C++. So it's like carpenters. Carpenters measure twice, cut once. That's what I do. I think in two different paradigms, two different implementations, and if they match, then I have done the right thing. But mostly I think in Haskell. Mostly I think with the mathematical properties of what is involved. Yeah? So earlier in this talk, I showed you this particular code, trivial filter being considered as a fold. And that fundamental operation can be translated trivially into C++. So C++ can do accumulations and folds and things like that. So that's good enough. Once I've understood my math, once I'm happy with it, once I've tuned my parameters, made them work in combination, spent weeks doing that, I can write the corresponding C++ in a day. Test it out, make sure the output of C++ is the same as that of Haskell, and I'm done. If there's a problem, I go back to my Haskell code, try things out first. That's my laboratory, not C++. And then there's a lot of real-world testing to follow from that. So since I have a little bit of time left, I will go into a demo. Here's a little bit of code that I have here. If I save my editor, it automatically triggers Haskell to create what I'm asking you to do. In this case, I'm showing you a track. The red dots, again, are positioned on a single-dimensional axis, and over time on the x-axis. So at time 50, my object stops being stationary and starts moving in a linear velocity. So there's an initial bit of acceleration, but then it starts moving in a linear velocity. And here's my trivial track I want to test against. Yeah? So the code in this case is quite simple and doesn't need much consideration. So check out. Here's my stationary filter. The way all this is happening is on the right-hand side, there's a GHCI daemon which automatically detects any changes to my code. As soon as my code changes, Haskell is rebuilt and we rerun the program, the simulation. So anyway, here's the same track, and now we have this blue line which shows how a stationary filter follows a linear object, which is poor. This particular line here refers to the velocity reported by the stationary filter. Well, the stationary filter can only report velocity 0, so that's not very valuable. But notice what I have done to achieve that. This is what I'm doing. Stationary position estimates is essentially my track filtered using the stationary filter. And then I view that track. Let's do the same thing with the constant velocity filter. And now, in this case, I have not shown the tracks, but now I see that the red line is indeed following the constant velocity object, but now we have also a velocity estimate of this object. I told you that the object remains stationary until time 50, and then it accelerates a bit. So you see that velocity is taking some time to catch up, and that's not good enough. I can change my filter to have a different parameter, and now the velocity is being estimated much better or much faster. But it is more noisy. And that's the trade-off that I make all the time. Notice that in the first 50 units of time, the velocity estimate is still wiggly, which is not nice because I kind of know that the object is stationary. What I could do is I could say combined filter. In this case, I've made a composite filter which has the properties of both stationary and linear velocity filter. So you notice that until time 50 or a little after that, the velocity estimate is exactly 0. And then it rises quickly following the constant velocity filter and then tracks the object. Yes, we have run out of time. I just wanted to say that in all this time, I have simply been replacing the initial state with a different type. Every filter that I've shown you is essentially following the same type class. So my code, depending on which initial state I use, my filters automatically get picked. Haskell allows me to be generic, and essentially it has been a joy to program in Haskell. I've really gained. I mean, not only my code reads better, I think better when I think in Haskell. Thanks a lot.